When composing images of 3D scenes, artists often change the projection from object to object. Such changes can help convey the dramatic intentions of the artist, make the scene easier to understand, or communicate information about the structure of the scene. In this video, we present interactive methods for creating multi-projection images and animations. This multi-projection still life was created with our system. The user can attach local cameras to different portions of the scene geometry. In the right window, we show the scene in plan view with a wireframe frustum for each local camera. In the left window, we show the multi-projection image. When we select a local camera, the attached geometry turns green, and the local camera view is shown in the right window. Notice how the local camera view differs from the multi-projection view. We can interactively adjust the parameters of any camera. This scene has 10 local cameras, and the multi-projection image updates at several frames per second. Composing such images is fast and easy with our interactive interface. We have designed several camera constraints that can help the user in adjusting the parameters of local cameras. With a wide-angle camera, curved objects can appear unnaturally stretched. Our direct orientation constraint reorients a local camera so that it points directly at the center of the geometry attached to it. In the bottom window, we see the scene from the left column's camera. We can animate the scene with this constraint in place. We use a different local camera for each column and one more for the floor and ceiling. For comparison, we show the same animation using a single camera in the bottom window. In the top window, the constraint is separately enforced on each column camera on every frame of the multi-projection animation. Normally, as we move the camera, the object moves in the image and different parts of it become visible. Using the fixed position constraint, the object remains stationary in the image plane, but we see different sides of it. Notice how the frustum shears in the right window, creating an off-axis projection. When we use the fixed view constraint, the object moves around the image plane, but we always see the same parts of it, like a sprite. Here we apply the fixed view constraint to the foreground cars. The exaggerated projection for the background emphasizes the depth of the scene. Notice how different parts of the background buildings become visible during the animation, while the views of the foreground elements remain fixed. In the single perspective animation on the bottom, the face of the red character is not visible during the initial conversation. Notice how in both animations, the blue car rotates before and after passing the red car. The fixed view constraint affects only translations, not rotations. This is a relatively complex combination of 2D and 3D. If the blue car were a simple sprite, it would only change in size. We can use multiple oblique projections to create an artificial sense of perspective. In the left image, the receding parallels of all the obliquely projected buildings point towards a central vanishing point. More of the city is visible, and it is easier to judge the relative sizes of the buildings in the multiple oblique view. For instance, the pink rooftop in the upper right corner is about the same size as the gray one next to it. In the true perspective view, it appears much larger. On the left is Giorgio de Chirico's Mystery and Melancholy of a Street. On the right is our reconstruction. In our interactive system, we see the entire scene from each local camera. De Chirico used a different projection for each object in the scene to create the melancholy aura of the long receding path. We used our system to animate the van. The occlusion relationship between the van and the brown building is automatically resolved. The master camera animation on the right shows that the van's path is actually straight. It appears curved in the multi-projection animation because the van's local camera rotates as it moves from left to right. Not every motion is as visually pleasing since the motion parallax can conflict with the perspective and occlusion information. Here, in our interactive system, we move the entire scene. Since the local cameras are all different, the objects move and scale at different rates. Despite these issues, multi-projection rendering allows us to create a variety of effects that are impossible with standard single projection rendering.